Hey everyone! I hope you brought your gloves because today we're going to be working with ice tables! Yay! Anyways, you're probably wondering, what is an ice table and when do we use it? Well, an ice table is basically a simple way to calculate your K expression. And since today we're talking about Kp, this will become very useful. Now, the equilibrium constant. Let's talk a little bit about it. Well, the most common K equilibrium constant that you've probably learned is K equilibrium, or Kc. And this deals with the concentration of your products and reactants. Well, today we're going to be dealing with Kp, which deals with the equilibrium constant dealing with pressure. So let's get started. Alright, so there's some background information that you need to know before we start some problems. Now, you've probably learned that K equilibrium, or Kc, equals the concentration of your products divided by the concentration of your reactants. Well, it's a little different for Kp, but it's written in the exact same way. Now, what I've just told you is that Kp is the equilibrium constant dealing with pressure. So, to write the equilibrium expression for Kp, you would simply say Kp equals the partial pressure of your products divided by the partial pressure of your reactants. So let's say you have a reaction, very simple, A yields B. How would you write your Kp expression? All you would say is Kp equals your partial pressure of B divided by the partial pressure of A. And it's as simple as that. Except for one thing. You need to remember one important aspect of writing K expressions, whether it be Kp, Kc, anything. And that is, never include pure solids and liquids in your K expressions. Now what I mean by this is, let's say you have this same reaction as I mentioned before, A yields B. Let's say it's solid A yields gaseous B. Well, we said never include pure solids and liquids. So, if this were the case, A is solid and B is gaseous, then when writing your Kp expression, you would not include your reactant A in your Kp expression, so your Kp expression would simply read Kp equals the partial pressure of B, and that would be it. And another thing that you need to remember is when you're writing your Kp expression, the units of your partial pressures need to match all throughout the expression. For example, if you had atmospheres as the units for your products, you want to have atmospheres as the units for your reactants as well. It just keeps it constant. Now let's move on to what the main thing we want to talk about is ice tables. Now, the question in your mind right now is probably, what do these letters mean? Well, this is what they mean. It's very simple. Ice tables are basically something that you use to calculate pressure, concentration, what have you, as a reaction is approaching equilibrium. So, some questions might give you the initial concentration or the initial pressure of something, and they want you to find the equilibrium pressure, or they want you to find Kp. Well, what you know is that Kp, or a K expression, is something at equilibrium. So obviously you're going to want to have, or in this case Kp, you're going to want to have the pressures at equilibrium. So if a question gives you the initial pressures, how are you going to find this? Well, use an ice table. And that gets me to what the letter stands for. The I in ice table stands for initial, in this case initial pressure. The C in ice table stands for change, and in this case, again, change in pressure as the reaction approaches equilibrium. And the E in ice table stands for equilibrium, in this case, the pressure at equilibrium. It's very simple, and all you have to do is just plug in these values for each of your products and reactants, and finding Kp can come to you in a matter of seconds. Let's try an example. Let's say you are given the reaction 2 sulfur dioxide plus oxygen yields 2 sulfur trioxide. And they give you the initial pressure of sulfur trioxide is 3 atm, and the final pressure or equilibrium pressure of sulfur trioxide is 1 atm. And they're wanting you to find Kp. Well, again, we know that Kp is the pressures of the partial pressures of all your products and reactants at equilibrium. Well, let's start off and make sure that we don't have any pure solids or pure liquids in our reaction. All of these are gaseous, so we know that we can include all of them in our Kp expression. And the first step that you want to do when solving these kind of problems is writing your Kp expression so that once you find all your values, you can easily plug them in, and it will be very simple. So your Kp expression would be written as the partial pressure of your products divided by the partial pressure of your reactants. And exponents refer back to your balanced equation. So if you have a coefficient of 2, your exponent would be squared. So let's write the Kp expression. It's right here. Kp equals the partial pressure of sulfur trioxide squared divided by the partial pressure of sulfur dioxide squared times the partial pressure of oxygen. Now, let's move on to what we're trying to find. Again, we're trying to find the partial pressures of these things at equilibrium, but we're given the initial pressure of sulfur trioxide and the equilibrium pressure of sulfur trioxide. We don't know the equilibrium pressures of our reactants, so we're going to use an ice table. Very good. Now, let's go ahead and plug in what we're already given. We're already given our initial pressure to be of sulfur trioxide is 3 atm. So we can go ahead and plug that into the initial box for sulfur trioxide. And we're also given the final or equilibrium pressure of sulfur trioxide, which is 1 atm, so we can go ahead and plug that in. And just like your exponents in your Kp expression refer back to your balanced equation, so do your changes. You want the value of x to be some kind of change in pressure. But since you have 2 moles of sulfur trioxide and 2 moles of sulfur dioxide for every 1 mole of oxygen, you have to multiply these x's by 2 for those two things. And also, since you're given an initial pressure for your products, but you are not given an initial pressure for your reactants, you can assume their initial pressures to be 0. So, if you're given the initial pressure of your products, that means as the reaction approaches equilibrium, it will be losing pressure, and the reactants will be gaining pressure. So, therefore, the change in pressure for sulfur trioxide will be negative, and the change in pressure for sulfur dioxide and oxygen, your reactants, will be positive. So, this is why these are positive. So, it's easy to say that the equilibrium pressures of sulfur dioxide is 2x, and the equilibrium pressure of oxygen is x, as we have right here. So now, you can probably see that all you need to do is find x, because once you find x, you can plug it into all of your partial pressures and you can find them. So, if you look closely at your ice table, you can see that the ice part of your products, or sulfur trioxide, can easily be written into an algebraic equation to find x. Well, you are correct. So let's do this. Step 1, solve for x. So, we can say 3 minus 2x equals 1. And if you do this simple math, which I hope you are able to do, you should get that x equals 1, and since we said before that x equals the partial pressure of oxygen, we can say the partial pressure of oxygen is 1 atm. Now, we also said before that the partial pressure of sulfur dioxide is 2x. So, we can just plug in the value of x into this and find the value of, or the partial pressure of SO2. And if you do this, 2 times 1, very simple, you get that the partial pressure of sulfur dioxide is 2 atm. Now you are ready to, as Mr. Elegante would say, plug and chug. Since you already wrote your Kp expression before, you've made it very simple for yourself. All you have to do is plug in the partial pressure values that you have found along with the equilibrium pressure of your products that you have been given, and you basically made it very simple to find Kp now. So obviously you're given the partial pressure of your product, sulfur trioxide, is 1 atm at equilibrium. And we found the partial pressure of oxygen to be 1 atm down here, and we found the partial pressure of sulfur dioxide to be 2 atm down here. So all you have to do is plug and chug. So you plug in your values: 1 atm for your products, 2 atm for sulfur dioxide, and 1 atm for oxygen. Square what you need to square, and if you do all the math correctly, you should get 1/4 or 0.25 as your Kp. And what you need to know is that we don't usually include units in our K expressions or our K values, so all your answer is Kp equals 0.25. And it's as simple as that. So one thing I want you guys to remember that we've already said before is never include pure solids and liquids in your K expressions, and don't forget that all your units have to match. Alright guys, thanks for watching. I hope you're comfortable with calculating Kp, and I hope you have a great day. Thank you.